Hello, math analysis. We are looking at section 4.5 right now, which is on Hamiltonian circuits and paths. So as a review, you know from the last section that a path is a graph that begins and ends at different vertices. A circuit is a route that begins and ends at the same vertex. And what's different about Hamilton from Euler is that with Hamilton you must touch each vertice exactly one time, as opposed to Euler where you must trace over each edge exactly one time. So I'm going to go over the notes briefly for you. Here is an example of a Hamiltonian circuit. I'm going to touch each vertex exactly one time and return to the original vertex. So that is a Hamiltonian circuit. That is not unique. There was another one in here. If you want to see it, I'll do it in the pink. So instead of going up, I'll come down on this one, but in the bottom, I'll go that way. So that is an example of a Hamiltonian circuit. Now, one of the tough things about Hamiltonian circuits is that there is no way to guarantee for every single graph if one exists. However, they did come up with 3 conditions, and if these 3 conditions are met, then you're guaranteed to find a Hamiltonian circuit. So the first condition is that you need a connected graph. The second condition is you have to have more than 2 vertices. And the last condition is if you take the number of vertices and cut them in half, whatever that number is, if the degree is that number or more at each vertex, then we are guaranteed that we will have a Hamiltonian circuit. So we're going to take a look at 3 quick examples here. So our first condition, is it connected? Yes, it is. There are no vertices that do not have an edge connecting them to another vertice. The second condition, is there more than 2 vertices? Yes, there is. And the third condition, I count there's 1, 2, 3, 4, 5 vertices. 5 divided by 2 is 2.5. And if I go around and I determine the degree at each vertex, I do notice that it is greater than the half of the number of vertices. So that means yes. So all of the conditions are met, which means I'm guaranteed to find a Hamiltonian circuit. And for those of you who are wondering where it is, here you go. Start here, go there, come across, down, and up. There is an example of a Hamiltonian circuit. Okay, in the next example, let's check the conditions. Yes, the graph is connected. Yes, there are more than 2 vertices. There are 5. Half of 5 is 2.5. But when I check the degree at each vertex, it is less than half of the number of vertices. So there's no guarantee that I'm going to find a Hamiltonian circuit, but I still have to look. And this has to be the easiest Hamiltonian circuit you'll ever run across. So this is the instance where the conditions were not met, but yes, we still can find a Hamiltonian circuit. Okay, so let's look at the last graph here. So yes, it is connected. Yes, there are more than 2 vertices. And there's 5. Once again, cut it in half is 2.5. And immediately I see, oh boy, this condition is not met because the degree is not 2.5 or greater. And when I try and find a Hamiltonian circuit and try and touch all the vertices, I cannot do that without returning to another vertex. So no, this graph did not have a Hamiltonian circuit. Okay, something else that we studied was the knight's tour problem. Hamilton was a knight, so it makes sense. And remember, if you don't play chess, a knight moves in the shape of an L. So here are 4 of the places a knight could end up. 2 to the right and 1 up and 2 to the left, 2 to the right and 1 down, or 2 down and 1 to the right. There's actually 4 more places the knight could end up. Why don't you try and see if you can figure that out for a second here? All right, hopefully you put the machine on pause, and now you'll see if you did it right. So your knight could also end up here, 2 up and 1 to the right. He could end up here. He could end up right here. He could end up right here. And there I have it. I think I have all of the positions the knight can end up. Okay, so one of the things we did is we looked at a chessboard, and we made a graph to model the chessboard. And so I'm going to put vertices right where all of the squares are. The vertices represent the squares on the chessboard, and the edges represent if the knight was at A, where could he end up at? So if he was at A, he could end up at E. He could also end up at G. If he's at B, he can end up at F. He could also end up at H. At C, he could end up at D. He could also end up at G. And at E, he could end up at F. And we have the other one, and D, he could end up here. So if we take a look at this, we start at any vertex, can we move around and touch every square on the chessboard? And you find out that yes, we actually can. And the final thing I'm going to talk about with section 4.5 is what a tournament is. A tournament will always be a complete graph. So what I'm going to do first is I'm going to draw this graph right here. There's 4 teams in the tournament, teams A, B, C, and D. And what I notice is that one of the rules is that we always point at the loser. So when A played B, B won, so we're going to point at the loser. When A played C, A won, so that means C lost. When B played C, B won, so C lost. When B played D, D won, so B lost. And when C played D, D won, so C lost. And when A played D, D won, so A lost. So looking at it, it's very easy to see who your best team was. They have no arrows pointing at them. The second best team has only 1 arrow pointing at them. The third best team has 2 arrows pointing them, and the last team has 3 arrows pointing at them. Yeah. So this is an example of a Hamiltonian path. We visit each vertex exactly once, and we end at a different vertex. So that, friends, is section 4.5.